presentation before we close for the day, and the session is product development. The first presentation is from Mr. Zaahid Imran, and the title, A Mobile and Portable Pre-ICU AM produced by BiPAP Ventilator System in response to Covid-19 challenges.
Good afternoon, everyone. I am Zaahid Imran, a design engineer at the Advanced Engineering Design Group at Nelson Mandela University. We're based in Port Elizabeth. I just want to say thank you for giving me this opportunity today to give you a small insight on our pre-ICU additively manufactured ventilator system. The ventilator is actually here. I have it on the desk here if you guys want to see. We've also got it available at the Rapid 3D stand if you guys want to have a small demo of how it works. The main focus of this presentation will be on the research, design, and manufacturing of our mechanical ventilator. Okay, so just before moving further, let's start off by looking what ventilators are. So a ventilator is a machine that helps the patient breathe if the patient is unable to do so by themselves. The machine pushes air into the lungs. It pushes air and oxygen into lungs, in and out of the lungs. These ventilators are normally referred to as mechanical ventilators or resuscitators, resuscitators. And the main function is to take over the breathing system of the patient while the patient is fighting off infection. A ventilator is essentially a pump delivering air by positive pressure to the patient. So when a person's lungs inhale and exhale air normally, oxygen is taken into the cells to survive, and carbon dioxide is expelled from the cells. A patient suffering from COVID-19 in severe cases has an inflamed airway, and this causes the airway to drown in fluids. Therefore, a mechanical ventilator in this case helps oxygen into the lungs at a rate required for normal breathing. So there are two main types of non-invasive ventilators. We've got our CPAP machine first of all, which basically stands for our continuous positive airway pressure. And the CPAP machine basically produces pressurized air at a continuous steady amount. And the basic disadvantage of a CPAP machine is that it doesn't sync with the breathing system of a patient. So basically, the patient is breathing out and the ventilator is pushing air into the body. This makes the patient very uncomfortable. On the other hand, we have a BiPAP machine. Sorry, I just forgot to move on the slide. So we've got a BiPAP machine, which stands for a bi-level positive airway pressure machine, which is basically essentially the same as a CPAP machine in the sense that it still operates. It still continuously supplies air and oxygen to the patient. However, it operates at two different pressures. It basically operates at a higher pressure inhalation and a lower pressure at exhalation. This is normally used instead of CPAP machines when a patient cannot tolerate the continuous pressure into them. Furthermore, BiPAP systems operate in sync with your patients, which basically eliminates the uncomfortable feeling you have with a CPAP machine. So, an early challenge for the first responders of the COVID-19 epidemic was the availability of the CPAP and BiPAP machines that were portable and easily to implement en route to the ICU. In response to the shortage of ventilators in the early stages of the pandemic, the need for design of a low-cost portable ventilator that automatically inflates and deflates the ambibag as per the requirements was initiated. Our ventilator is derived from MIT's open source ventilator platform that already meets the clinical requirements for medical respiratory device. Automating the procedure for compression and automating the procedure for compression seem to be the simplest strategies to satisfy the need for low-cost mechanical ventilation, with the ability to also be easily and cost-effectively manufactured at scale. So producing this via local additive manufacturing resources is obviously cheaper than obviously importing a conventional ventilator from, let's say, the US. So according to a report by News24, published in March of 2020, South Africa was underprepared for the serious escalation of COVID-19 cases, with roughly about 3,000 out of 7,000 critical care beds available between the public and the private healthcare sector. Furthermore, the SA Managing Director of Brother, a German producer of ventilators worldwide, stated that there were currently no suppliers who imported ventilator machines from various countries, including the US, Germany, and China. The sad reality is that there was a global undersupply of ventilators worldwide, and Africa, and by extension South Africa, was not on the top of the supply list. There was an estimated of 4,000 ventilators in the private healthcare sector and about half that number in the public healthcare sector. The Executive Director of National Association of Automotive Component and Allied Manufacturers, who was also busy with a ventilator project at the time, stated that not all the ventilators will be available to COVID-19 patients because obviously a lot of them are already in use with patients in the hospitals. Even if ventilators became an option, it was not going to be, it wouldn't be possible for South Africa to import these machines into the country because obviously there was a no-fly there was no-fly rule, so basically we couldn't import or export countries in and out of the country. So now let's take a quick look of how this ventilator project was initiated. In the early stages of the coronavirus pandemic, a student-run startup by the name of HSA took the initiative to join the Emergency Ventilator Response Team, a consortium formed to provide solutions in response to COVID-19 pandemic. The first mission was to create a low-cost, easy-to-manufacture automated resuscitator to help meet the growing demands of the coronavirus pandemic, the ventilator shortage. So HSA initiated this project on the 22nd of March 2020 and developed the low-cost, non-invasive, easy-to-use pre-ICU mechanical ventilator. At that stage, there was still a significant scope to get the ventilator to a more advanced level of sophistication with regards to research and development. And to achieve this, the Advanced Engineering Design Group applied for funding from merSETA, and this was thankfully approved. The aim of the funding was to provide continuity to the project in respect to the design, and to take the current ventilator to a new level of sophistication as a fully functioning BiPAP device. So as mentioned before, the ventilator was derived from MIT's open source ventilator. However, our first concept started off with a single pusher arm system that inflated and deflated the ambibag. The pusher arm had a flat and large surface area to ensure maximum deflation. A major problem with this configuration of the pusher arm was that as the pusher arm engaged with the ambibag would basically go into the base of the pusher arm, and that would cause a restriction on the airflow out of the ambibag. So the next iteration consisted of a dual pusher arm system, and this consisted with a dual pusher arm system with a much finer rack and pinion system. And the arms had a more rounded piece of material that bulged out of the top face of the pusher arm. This eradicated the curling issue that we faced with the initial prototype. From this point onwards, a series of optimization processes were carried out on the ventilator systems. I can just show you, we have all our we have 6 versions of the ventilators. However, the final ventilator in its final form consists of a 2 pusher arm rack and pinion system, which is activated by a servo motor. The plumbing system consists of circuit tubes for airflow, a pop-up valve to ensure that the maximum pressure within the system is not exceeded. We've got a PEEP valve to ensure back pressure within the system. The electronic system consists of a microcontroller and an HMI that allows you to basically adjust all the variables and settings that you need to adjust when adhering to patients. So most of the parts on the ventilator system are additively manufactured in Onyx, which is a composite of microcarbon fiber filled nylon. The reason we chose this material is that it offers a high strength, toughness, and chemical resistance when printed alone. And furthermore, it can also be printed with reinforced continuous fibers such as fiberglass, carbon fiber, and Kevlar. And when you reinforce the Onyx with these added materials, you can get aluminium strength based parts. So all the parts on the ventilator were designed considering the design for additive manufacturing using Onyx, and were all printed on our state-of-the-art Mount Forge desktop AM machine. Parts were also designed keeping in mind the need for injection molding in the future if mass production became an option. All parts on the ventilator system were designed, moving on to FEA verification. The most important aspect of this ventilator system is the push arms, as this is the system that basically inflates and deflates the ambu bag. So we therefore performed FEA verification tests to ensure that, to basically validate these parts. So linear static simulations were performed with the boundary conditions set at the worst case loading scenario. The pusher arm at the worst case loading scenario, that the push arm will ever experience. So as we can see on the picture on the top there, we've got pressure applied to the pressure plates that are in contact with the ambu bag. We've got constraints applied to the railings and also to the gear mesh where the rack is in contact with the gear. Moving on, we can see that studies have proven that a high stress area was confirmed on the rib of the push arm. Therefore, a mesh refinement was performed on these filleted areas with tandem. So a mesh refinement was performed on the rib areas, and this was obviously done with a global mesh size. A convergence study was also carried out in the high stress zone, and all studies proved to be within 5% error margin, and thus conversion was assumed to be achieved. Moving on, it is important to note that also the safety factor that occurs in the compression location zones the safety factor occurs in compression zones, which basically means that fatigue failure is not a problem in that area. Also, the composite nature of Onyx is that the material has built-in crack arresters in the form of short carbon, whilst the nylon matrix also has a recognized excellent fatigue and impact resistant properties. The data extracted from our FEA results are tabulated in the table above. The pusher arms has a small deflection of 0.456 millimeters off the original position. Now, deflection on our pusher arms is not a desirable property, because if our pusher arms deflect, that means that our pusher arms are not operating at the most efficiently, efficiently. Therefore, a more rigid structure is desirable. Nonetheless, the deflection will never occur continuously, in everyday motion, as we have programmed the system to never operate at the worst case loading scenario. Furthermore, we can see that the pusher arms has a minimum safety factor of 12.377 at the high spot, meaning that the possibility of failure at this location is minimal. The stresses are almost all occurring at locations where the compressive stresses are dominant, which influences the factor of safety results. Since the compressive stresses do not result in fatigue failures, these compressive zones of failure are not important and therefore do not have any significant design impact on the component. The results dictate that even under the over-conservative testing scenarios, the pusher arm will still perform optimally without failure under any reasonable circumstances. The initially selected concept design push arm was adjusted during the design process to accommodate the standards of industry to allow for more dynamic, customizable design with further reaching applications. From all the tests and calculations and simulation studies, it has been proven that the pusher arm has more than adequate strength and therefore has passed all the necessary specifications needed to be used in a component in the ventilator assembly. Finally, a huge thanks and appreciation must go out to all our collaborators, and a huge thanks to merSETA for funding this project. Thank you.